Start recording. So this question asks for concavity, and most people got to the right. The first thing that I want to make sure you guys are doing is, because the numerator is just a constant, you should definitely rewrite that like that. Okay? You do not want to derive the you don't want to do the quotient rule if the top is just a number. Rewrite it. Even if this was, I know it's not, but even if this was a 4, just put the 4 out front like that and derive it like that. Okay? So it doesn't matter. Now, if the top was an x or something, now I'm definitely going to do the quotient rule. Okay? But if it's a number, the quotient rule will work. Don't get me wrong. It's just way more complicated. If you do that, now it's just power rule and chain rule. F prime of x is negative, comes all the way out front. X squared plus 1 to the negative 2 times 2x, which is going to become negative 2x over x squared plus 1 squared. You guys okay with that? All right, so if we had to do, let's just do the first derivative stuff with this too, just to get practice with that, okay? So the only thing that makes that equal 0, again, we want to look at where is the numerator 0 and where is the denominator 0. Those are going on my number line. Okay? Now again, this is for increasing, decreasing, which is not what this question asks, but just so we get the whole process. So x equals 0 is a critical value because it makes the derivative 0 and it's a point on the function. X squared plus 1 is never ever 0. Okay? So the only number that's going to go on my first derivative number line is 0. And we're going to check those intervals. Okay? If you plug in a negative number to your derivative, you're going to get a positive over a positive, which means this is positive and f is increasing there. If you plug in a positive number into your first derivative, you're going to get negative divided by a positive, which is a negative, which means it's decreasing there. And we have a relative max at 0, comma, and I can't remember when you guys did this here. Like, if you're finding the y value, you're going to plug it back into the original function always. When you do that here, you get 1. Is that okay? And increasing, decreasing will be intervals there. I'm not going to list them out, but we can do that. Okay. Now we got to drive this thing again. So let's draw a big line here. And something I told you in class here, I know it was probably quick. Anytime you derive a fraction and the denominator is squared, like the whole thing is squared, like in this case, x squared plus 1 squared, when you do the quotient rule, one of those things is going to cancel out. Don't multiply everything out first. Cancel one of the x squared plus 1s out. So when we do the quotient rule, it looks like this. It's a low d high minus high d low, which to derive that we need the chain rule. So that's 2 x squared plus 1 times 2x. And that's all over the denominator squared, which makes it x squared plus 1 to the 4th. It's okay? All right, now remember I told you, one of these x squared plus 1s is going to cancel. There's 3 basic terms up here. Let's switch colors here, just so we can see this a little bit easier. There's the low d high part, there's the high d low part, and there's the low squared. Every single one of them has x squared plus 1s. So we can cancel out the least of them. The least of them is always going to be in the high d low part, which is over here. There's 1. So this is going to cancel out. Now remember, you're distributing this division to both of these. So it cancels out 1 on the right side, it cancels out 1 on the left side, and it cancels out 1 in the denominator. That's how fractions work. Okay? So that it allows me to not have to square out that x squared plus 1 up there. Now it's just x squared plus 1. Let me write what we got. Okay, now it's just x squared plus 1 times negative 2 plus 2x times 2 times 2x all over x squared plus 1 cubed. Okay? We want to factor out the top. So we got to get everything up there factored out. So we need to expand it before we can do that. So we're going to get negative 2x squared minus 2 plus 8x squared over x squared plus 1 cubed. And that's going to boil all the way down to 6x squared minus 2 over x squared plus 1. And I think like, you had that. You didn't cancel out the x squared plus 1, so it was harder to factor. Okay. So here we're going to factor out a 2, and that becomes 3x squared minus 1 over x squared plus 1 cubed. And everybody knows that if you have a difference of 2 squares, which is what this is right here, okay, the 2 is just chilling out there. He's not hurting anybody. You take the square root of the first thing minus square root of the second times square root of the first plus square root of the second. Anytime you have something, so this is just this case here, man. X squared minus 9 is going to factor into the square root of x squared minus the square root of 9. Like, this is almost automatic. You're so used to seeing this, right? Like, you don't even need that step. You do x minus 3, that's a 3, x plus 3. Okay? If they're uglier things, it doesn't matter. You're just going to get the square roots of them. So we get the square root of 3, x minus 1, and the square root of 3, x plus 1. And that's all over x plus 1 cubed. Okay? And again, that denominator, you can't factor it. It's never, ever going to equal 0.
Could you just leave it as 3x squared minus 1 and set that to 0?
That's the same thing. I really think factoring is a little better because then when you plug it in, you can see where all the positive negatives are. But yeah, as long as you're careful, that's going to work. Okay? So our number line for the second derivative has to have a negative 1 over root 3, which you can rationalize to negative root 3 over 3, but it doesn't really matter. They're the same number, okay? And we're going to have a root 3 over 3 or just a positive 1 over root 3. Now, I don't know what numbers they are exactly, but I know a number less than that will definitely be like negative 10. Okay? So you can plug negative 10 back into your second derivative because we're checking down here. Here's negative 10. We're going to plug that back into my second derivative to see if it's positive or negative. Okay? If you plug it into the up here, you're going to see that it's positive over positive easily. Okay? If you plug it in down here, you're going to get a negative times a negative, which is a positive over a positive. So it doesn't matter which one you do, it's positive. Now that doesn't mean increasing anymore. That means that we are concave up there. A number between the zeros is 0. Plug that in, you get negative 1, negative 2 over 1, which is negative, which means on that interval, concave down. And if you plug in a number bigger than 1 over root 3, like a million, you're going to get positive times a positive over a positive, which is a positive. Okay? So then to write all this junk out, you can see that it is concave up from negative infinity to negative 1 over root 3, union with 1 over root 3 to infinity. It's concave down from negative 1 over root 3 to 1 over root 3. And our points of inflection are going to happen where the concavity changes sign. There's 2 of them. There's one at negative 1 over root 3, and there's one at positive 1 over root 3. Okay with that? We just got to find the y value, which means we go all the way back to the beginning. If you recall, f of x was 1 over x squared plus 1. So if you plug in 1 over root 3, you're going to get 1 over 1/3 plus 1. But that's just 1 over 4/3. And 1 divided by a fraction is just its reciprocal. That's the same thing as saying, instead of 1 divided by 4/3, that's 1 times 3/4. Same thing. So you get 3/4. If you plug in negative 1 over root 3, because you're squaring it, you get the same thing. Cool? And honestly, something that I skipped over from the beginning and something I've been trying to talk to you guys about in general is if, let's just stay down here with all this junk, is if you have a function like this, like I'm hoping you kind of know what that looks like a little bit. You know what the horizontal asymptote of that thing is? It's not 1. The bottom's going to get way bigger than the top. The bottom is like going to be a huge number squared. That's going to go to 0. All right? Those are rules that you're supposed to know. There's a horizontal asymptote at 0. There's no vertical asymptotes because the denominator is never ever 0. So all we know is this graph is flat over here and it's flat over here. Make sense? And all it does is ride along this asymptote. It's going to be flat like this. If you want to know, you can plug in a few extra x values, but just plug in 0 and see what the y. Remember, we always talk about this: horizontal and behavior, vertical asymptotes, x-intercepts, y-intercepts. If you can get those 4 things on a graph, you should be able to kind of trace at least a little bit of what it looks like. Okay? This thing has no x-intercepts because the top will never ever equal 0. But if you put 0 in, you get 1. That's the y-intercept. So all I know is this thing has to go to that point and then go back down. So it looks like this. You can see it's concave up, concave down, concave up, which is exactly what our second derivative number line told us. Okay?